we are given that work done equals to the force times the change in distance. The change in distance can be written in its calculus form from 0 to x. And we know that for spring, F equals kx, and the proof for this formula is a different story. We're just applying what we know. Now we can solve this integral very easily to obtain half kx squared and F equals kx, so we can replace kx with F and we end up with half fx. So this is the calculus method of deriving the formula, and now we'll move on to the intuitive method. Calculus is a pretty reliable way of deriving formulas, but it's usually not very intuitive or visual. I'm unable to directly understand EPE, like the bonds between atoms in a spring, to calculate the energy potential in that. But then you realize that to calculate the total energy in a system, you can look for the total input energy. If you imagine an empty flat ball with no resistance, no frictional resistance or no air resistance, and we have a spring attached to a bump in the ground, and a block some distance away from the spring of infinite spring constant, meaning that this block cannot be squeezed. Now we accelerate the block towards the spring, but we accelerate like maybe a little bit only now to give the block some velocity, and now the block is just sailing at a constant speed towards the spring. We focus on what happens to the forces on the block. When it is compressing the spring, the block is observed to experience a linear increase in force in the opposite direction of the motion, meaning that it indicates a loss in energy. Because work done, if your force is in the opposite direction in the distance, then it means energy is being lost. And we can say that the linear increase in the force is due to the nature of F equals kx. As x increases linearly, F increases linearly too. The rate of increase of x does not affect the energy transfer. The block might be compressing the spring at a different rate. Like for example, in the beginning of the compression, it might be compressing faster than at the end. It does not affect the energy transfer since work done is only equals to force times distance and does not take time into account. We can investigate the work done by drawing a graph of force against distance. Let's say we have force F applied on a spring. This force pushes the spring a very short distance before the force increases. We can let the distance the force F pushes to be denoted by epsilon, where epsilon has an infinitely small value. The work done onto the spring would be F times epsilon. But now since F equals kx, when x increases, F increases by epsilon with k. And now this force again pushes the spring a very short distance, which is epsilon, before it increases even further repeatedly. We notice that the change in distance is of equal value, and so is the force. Hence, the total work done can be written as such, where x is the total distance stretched or compressed, and F the largest force applied on the spring, and n to denote infinity, since epsilon has an infinitely small value.